Welcome. Today we will discuss dynamic model of induction motor in synchronously rotating reference frame and stationary reference frame. So, let us consider this figure. So, we have the d axis and q axis which and dq reference frame is rotating at synchronous speed omega e, hence its name is synchronously rotating reference frame or synchronous frame, and the 3 phase stator winding is made equivalent to two stationary coils ds and qs along d axis and q axis, and the 3 phase rotor winding or the rotor winding is made equivalent to two windings dr along d axis and qr along q axis, r for rotor, s for stator and dq reference frame, direct and quadrature reference frame. So, the 3 phase windings are made equivalent to two windings in d and q axis, and for stator and rotor you have two windings. So, the reference frame is rotating at synchronous speed omega e and rotor is rotating at speed omega r, rotor speed is omega r, and the voltage equations we will first consider. For the stator winding, the voltage across the stator winding is VQS, that is equal to resistance drop in the winding, that is RSIQS, plus induced EMF along the same winding. And as you know, EMF induced is of two types, one is rotational EMF, another is transformer EMF. The transformer EMF, as you know, it occurs in the transformer and stationary, when the stationary coil links with a time varying flux, the transformer EMF is produced, which is given by d psi by dt, and rotational EMF which is there in the DC machine is produced due to relative speed between winding and flux, conductor and flux. So, that is the rotational EMF. In AC machines, both these EMFs are there, transformer EMF and rotational EMF. So, in Q axis stator winding which links with the flux psi Qs, the transformer EMF is d psi Qs by dt. Psi qs is the q axis stator flux linkage. So, d psi qs by dt is the transformer EMF. Now, the rotational EMF is given by omega E into psi ds. As the transformer EMF is produced by the flux linking, time rate of change of flux linking with the same winding, the rotational EMF is produced in q axis stator winding qs due to a flux at 90 degree. In DC machine, when the flux is along the d axis and armature EMF is induced along the q axis, armature winding is equivalent to a winding between the brushes, and brush axis and pole axis are 90 degree apart. So, along between a winding between the brushes, EMF is induced due to flux along the d axis. Similar, q axis stator winding is just equivalent to armature winding of DC machine, and d psi ds is the d axis stator flux, which is equivalent to pole flux of the DC machine. And like DC machine, as DC machine V equal to R I plus E B. So, E B is here omega E into psi ds. So, here plus sign. And similarly, voltage along the d axis stator coil VDS is RS IDES, the resistance drop, plus transformer EMF along d axis stator winding is d psi ds by dt, and rotational EMF is omega E into psi qs, because psi qs is at 90 degree with the winding, and this sign will be negative, because psi ds and psi qs are at 90 degree. In one rotational EMF due to one flux is positive, rotational EMF another flux is negative. So, due to psi ds it is positive, because psi ds is the direct flux, direct axis flux, and so EMF it is positive, and EMF rotational EMF due to quadrature axis flux is negative. Similarly, voltage in the q axis rotor winding VQR is resistance drop RIQR plus transformer EMF is d psi by dt with for the same flux linking with the coil, and rotational EMF is here is omega E minus omega R into psi d r, because we are considering q axis rotor winding psi qr, q axis rotor winding qr, EMF will be induced due to psi dr, and relative speed between the winding and the flux linkage is omega E minus omega R, because reference frame is rotating at omega E and rotor is rotating at speed omega R. So, relative speed is omega E minus omega R. So, transformer EMF is omega E minus omega R into psi dr. Similarly, voltage along the d axis rotor winding is VDR, that is RR into IDR, resistance drop, transformer EMF is d psi dr by dt, and rotational EMF is minus omega E minus omega R into psi q r. So, as I have mentioned here, I QS or IDS, these are q axis and d axis stator current. So, similarly, all the terms are can be defined, and one is these are the equations. So, let us number, this is equation 1, this is equation 2, this is equation 3, this is equation 4. Then flux linkage equations, psi q s is cell flux, Ls I q s is the cell flux, then mutual flux from the rotor current. Psi q s is the total flux linking with the q axis stator winding q s, that is cell flux due to the current I q s and inductance L s, and mutual flux from q axis rotor current I q r, and mutual inductance between stator and rotor is L m. And psi d s is similarly L s I d s plus L m into I d r, and similarly psi q r is L r I q r, cell flux due to q axis rotor winding plus mutual flux from q axis stator winding, and psi d r is cell flux L r I d r plus mutual flux is L m I d s. So, there will be mutual flux between the stator and rotor along the same axis. There is no mutual flux between D and Q axis, because D and Q axis are at 90 degree, there will be no mutual flux between D and Q. So, there will be mutual flux between the stator and rotor. So, here you can write L m is the mutual inductance between the stator and rotor, and L s equal to self inductance of stator. Self inductance is sum of the leakage inductance plus mutual inductance. This is the leakage inductance of stator. Similarly, L r is the self inductance of rotor, that is leakage inductance of the rotor plus mutual inductance between stator and rotor. So, you can write mutual flux along D axis, that is psi d m, that is L m I d s plus I d r, and mutual flux along q axis, that is psi q m, that is L m into I q s plus I q r. So, we have psi d s is the self flux of the stator, that is L L s into I d s plus psi d m, and psi q s is leakage flux linking with the stator plus mutual flux. Similarly, psi d r is L L r I d r plus psi d m, and psi q r is a leakage flux psi L L r I q r plus psi q m. These are auxiliary equations. This can be used and they can be derived. So, now using these flux linkage equations in the voltage equations 1, 2, 3, 4, we can represent the voltage current relationship, which is VQS, VDS, VQR and VDR, voltages along the across the 4 windings, that is equal to one matrix into current vector is for VQS corresponding current is IQS, for VDS corresponding current is IDS, for VQR corresponding current is IDR, IQR. IQR and for VDR corresponding current is IDR. So, VQS is RS into IQS plus d psi QS by dt. For d psi QS by dt, you replace IQS is LS IQS. So, we have S LS into IQS and SLM into IQR, then plus omega E into psi ds, and omega E is LS IDS. So, we have omega E LS IDS and plus LM IDR. So, omega E LM IDR. Similarly, VDS second row VDR DS is RS IDS plus d psi ds by dt, d psi ds by dt S LS IDS and SLM IDR plus SLM IDR, then minus omega E psi QS. Psi QS is LS IQS plus LM IQR. So, we have minus omega E LS and minus omega E LM. Similarly, VQR is RR IQR plus d psi QR by dt, d psi QR by dt is SLR IQR plus LM IQS. So, SLM IQS, then plus omega E minus omega R into psi dr, and psi dr is omega E minus omega R term is there, psi dr is LR IDR plus LM IDS. Similarly, VDR last row VDR is RR IDR plus d psi dr by dt, psi dr is LR IDR plus LM IDS, and then minus omega E minus omega R into psi Q R, and psi Q R is first this is minus omega E minus omega R, psi Q R is LR IQR and plus LM IQS. So, this is a vector matrix relationship. Left hand side of the equation is voltage vector, at the right hand side we have the current vector. So, voltage equal to impedance into current. So, this is the impedance matrix Z matrix, and this model is the impedance model, and this can be solved for the applied voltages VQS, VQDS, VDR, VQR. We can to solve the currents, and from currents we can get flux linkages. Here S is the Laplace operator, and for motoring operation as for motors the rotor winding has to be short circuited and rotor winding has to be closed. So, VDR equals to 0 and VQR equals to 0. D and Q axis rotor voltages are 0 because rotor circuit is closed, short circuited for the motor operation. So, we can use in this matrix equations VDR, VQR 0 and corresponding to the 3 phase supply voltages, 3 phase sinusoidal voltages VQS and VDS will be DC voltages like as we did it in the last class. VQS is Vm cos phi and VDS is V minus Vm sin phi, DC voltages. Phi is an angle, initial phase angle and Vm is the peak value of the phase voltages. So, VQS, VDS are DC voltages and using these equations the currents can be solved, current expressions, current transients can be found out, IQ as a function of time and from current flux linkages can be obtained and from current and flux the torque can be obtained. Torque. So, as you know electromagnetic torque T E is produced by the interaction of the flux and current. So, we have T E vector, let us treat it as a vector, 3 by 2 comes for the reference frame transformation, reference frame multiplier, P by 2, P is the number of poles, this comes because number of pole pairs have to be considered to be multiplied and the expression is mutual flux cross rotor current, because rotor conductors gets force in the air gap flux. So, torque is produced. So, torque is 3 by 2 into P by 2 into psi m cross I r. Psi m is the mutual flux, I r is the rotor current and as you know psi m is the mutual flux, that is psi q m minus j psi d m and I r is the rotor current, that is I q r minus j I d r. So, using this you can prove the magnitude of the electromagnetic torque is 3 by 2 P by 2 and multiplied by psi d m I q r minus psi q m into I d r. It is an axial vector along the axis. So, this is the magnitude of the torque. So, in this expression we used air gap flux psi m mutual flux and rotor current I r. So, we got this equation for torque. Same way we can use other flux and other current expressions and we can get several expressions for the electromagnetic torque like this. This is one expression where we have used stator current components IQS and IDS. So, these are several expressions for the torque obtained in the same principle. So, for using different variables, like first equation uses mutual flux components and stator current components as variable. Second equation uses stator current components and stator flux linkage components as the variable. Third equation uses rotor flux components and stator rotor IQR, sorry. Third equation uses rotor current components and rotor flux linkage components as the variable, and fourth equation uses only current, stator and rotor currents as variables, and fifth equation uses air gap flux components and rotor current components as variable, and last equation uses rotor flux linkage components and stator current components as the variable. So, using any selecting proper variables, induction motor model can be expressed. So, 4 state variables are required. One is, so for it can be used for stator current components and rotor flux components can be selected as variables, and you can get one model of the induction motor. Similarly, stator flux components and stator current components can be used as variables, and you can obtain a model. So, there are in this way different models can be obtained. Several depending upon selecting the proper variables, these models, any models can be obtained. So, these are the basic equations. Using this equation, any states, any model can be obtained, any specific model can be derived. Next, we will discuss dynamic model in stationary reference frame. So, in stationary reference frame, the reference frame is stationary, not moving. So, in synchronously rotating reference frame, the DQ frame was rotating at speed omega e. In synchronously rotating reference frame, DQ frame was rotating at speed omega e. In stationary reference frame, we set omega e to be 0. We set omega e to be 0, the speed of the reference frame to be 0. So, we use alpha beta reference frame with 0 reference speed, reference frame speed, alpha beta reference frame. So, accordingly, we get the voltage equations. In stationary reference frame, so V beta S for the beta axis stationary winding is R S I beta S voltage drop plus transformer EMF d psi beta S by dt. There is no rotational EMF because omega e is set to be 0. Reference frame speed is set to be 0, and V alpha S R S I alpha S plus transformer EMF is d psi alpha S by dt, and VQR is RRIQR plus d psi QR by dt and here rotational EMF is there and minus omega r into psi alpha r. Omega for synchronous rotating reference frame it was omega e minus omega r into psi dr. Now, omega is set to 0. So, minus omega r into psi alpha r. This is not q r, but beta r. Beta r. Similarly, V alpha r is r r I alpha r plus d psi alpha r by dt plus omega r into psi beta r. Similarly, this is also so r r V beta r is r r I beta r plus d psi beta r by dt minus omega r into psi alpha r. These are the four voltage equations in stationary reference frame. Then the flux linkage equations in the same way we write psi beta s is L s I beta s plus L r I beta r. Psi alpha s is L s I alpha s plus L r I alpha r. Psi beta r is L r I beta r plus L s into I beta s. Sorry. L m and psi alpha r is L r I alpha r plus L m I alpha s. This is L m I beta r, L m I alpha r. So, these are the flux linkage equations, and using these four voltage equations and four flux linkage equations, similarly all the any model in stationary reference frame can also be derived using these 8 basic equations. Then apart from the torque equation, there is a torque balance equation which is always to be used, that is electromagnetic torque T E equals to motor torque plus inertia torque, that is J d omega m by dt, plus if viscous friction is to be considered, this is B omega m if it is to be considered, and this omega m is the mechanical speed. So, if you want to use the electrical speed, it is 2 by P J d omega r by dt plus 2 by P B omega r, because this omega r is electrical speed, that is P by 2 into omega m. Omega m is the mechanical speed of the rotor and omega r is the electrical speed of the rotor. Similarly, you can write omega e is P by 2 times the omega s. Omega e equals to 2 pi f. So, omega s synchronous speed is 4 pi f by p, and s is omega s minus omega m by omega s, that is omega e minus omega r by omega e. So, these are some basic equations which is to be kept in mind. Then we will have more detailed model of induction motor in synchronous reference frame with stator current and rotor flux components as variables. So, we used those basic equations for equations 1, 2, 3, 4 and use the flux linkage equations. So, that we can write, we can express d psi dr by dt, that is you can derive it, it is so we will have a model of the induction motor with stator current components, that means IDS, IQS and rotor flux components, that means psi dr and psi qr, stator current and rotor flux components as the variables. So, this is the state vector, you can take it, consider it as transpose. So, this is the state vector, using this we want to have model, and so using these equations, using the basic equations, we can simplify the using these variables and we get this equation for the rotor flux linkage d psi a dr by dt. This equation can be obtained, this equation can be derived. Let us number this to be equation number, let us further write, this is, let us write, this is equation number 5 and similarly d psi qr by dt is rr So, equation 5 and 6 give how the rotor flux components psi dr and psi qr change with time in terms of rotor flux components as well as stator current components. So, these equations can be solved dynamically to get how the flux builds up in d and q axis rotor windings. Then using in the same variables and using simplifying the original equations, we can get so you can write what is psi d, let us write what is psi ds. Psi ds is nothing but ls ids plus Lm by Lr psi dr minus Lm square by Lr ids, you can derive it. So, this you can write Ls whole into 1 minus Lm square by Ls Lr IDS plus Lm by Lr psi dr, and this is sigma Ls IDS plus Lm psi ds by Lr, where sigma is 1 minus Lm square divided by Ls by Lr is the leakage coefficient and sigma Ls is the LLS that is the stator leakage inductance. And stator self inductance LS is LLS plus LM, mutual inductance. Sigma is the leakage coefficient, which is less than 1. So, equation 5 and 6 gives the rotor flux linkage transients, and using the in the same way we can write d I ds by dt This is equation 7 and this is equation 8. This equation 5, 6, 7, 8 can be derived from the original voltage equations 1, 2, 3, 4 and using flux linkage expressions and adjusting the variables and manipulating the equations. These equations 5, 6, 7, 8 can be obtained. So, with these equations 5, 6, 7, 8 and with these stator current components and rotor flux components as variables, we can get a state space model like this. Let us write IDS, IQS, D and Q axis stator current components and psi D R and psi Q are the D and Q axis rotor flux components. This is the state vector. So, x dot is d by dt of this equals to the system matrix is minus A1 omega E, A2 and A3 omega r, then minus omega E minus A1 minus A 3 omega r and A 2, A 5 0 minus A 4 omega e minus omega r, 0 A 5 omega e minus omega r minus A 4. This is the system matrix and the state vector into multiplied IDS, IQS, psi dr and psi q r plus 1 by sigma ls 0 0 1 by sigma ls 0 0 0 0 whole into VDS VQS. So, this is the state equation, this is the state vector x, and this is left hand side we have the x dot d by dt of x dot equals to, this is the system matrix A x and plus this is the control matrix B and this is the control input U, because the 3 phase stator winding is applied with a 3 phase voltage which is made equivalent to this VDS and VQS. So, this is the input vector, this is the VDS and VQS is the input vector and B is the control matrix. So, this is the state equation with stator current components and rotor flux components as variables, and this can be obtained, and A is the system matrix in which we have the variables A 1, A 2, A 3, A 4, A 5. These are the parameters, A 1 to A 5 are the parameters which I will define now, and we have the synchronous reference frame. So, we have omega e in the stator equations and rotor equations we have omega e minus omega r, the speed related terms. So, this is the equation, and this A 1, A 2, A 3, A 4, A 5 we can obtain from the equations 5, 6, 7, 8 which we have already written. So, we have A 1 is R S L R square plus R R L M square divided by sigma L S L R square. A 2 is R R L M divided by sigma L S L R square. A 3 is L M divided by sigma L S L R. A 4 is R R by L R and A 5 is R R L M by L R. These are the parameters in terms of machine parameters, and this is the state space model and which can be simulated, and if you simulate these equations you can get say the torque versus speed graph. Normally you know at steady state conditions it is like this, but if you do the transient simulations you can get some oscillations like the high frequency oscillations like this, you can get it. Now, you simulate it and get this result. Thank you for attention.